Copyright University of Auckland, all rights reserved. The content and delivery of lectures in this course are protected by copyright. Material belonging to others may have been used in these lectures and copied by and solely for the educational purposes of the university under license. You may record the lectures for the purposes of private study or research, but you may not sell, alter, or further reproduce or distribute any part of these lectures to any other person. Failure to comply with the terms of this warning may expose you to legal action for copyright infringement by the copyright owner and/or disciplinary action by the university.
Thank you very much indeed for having me, and what a treat turnout. Thanks very much indeed for coming. I'm going to talk about something very, very simple, but in my view very, very important. And we're going to talk about graduate education, and graduate education particularly. This is a running order for the lecture. So we're having a bit of introduction now. This slide will appear again, so I know where I am in the lecture. Now, if you're a young graduate, or anybody going to apply for a job, the interviewer, the employer, isn't really interested in what exams you've passed. What he's interested in is what can you do, and come in, you're not so late as it makes any difference. We're only on slide 3. He's not interested in what exams you pass and stuff like that. He's interested in what you could do for the company. So as an academic, without giving away too many trade secrets, the average pass mark is at just over 50, you know, which means the average student knows a little bit more than they don't know. It gets worse. And they can only do 5 out of the 8 questions anyhow, and the 8 questions only cover part of the syllabus, and as soon as they pass their exams, they studiously forget everything they were ever taught. So you essentially starting from scratch and passing exams. What you as employers want to know is what can they do, and this is what I'm going to be dealing with in this lecture. So this talk is about the minimum that graduates in civil engineering or engineering geology, but not masters, can do. And doing something is the only test of ability. So when employers interview students, I wonder what they interview applicants for a job, I wonder what they talk about. Does the prospective employer give the applicant a piece of paper and say, the ground has an undrained strength of this, the loader says design a foundation for me? Because that's what they should be doing, because that's what they want these people to be able to do. This talk is not about teaching teachers how to teach, or students how to learn. One of the things I did learn a while ago was when one of my children decided to be a school teacher, and in the UK you have to have a qualification. And one of his courses in that qualification was educational psychology. So I had a 1-hour crash course in educational psychology, and I'm now an expert. And one of the things I learned was different people learn in different ways. Some people learn best by the formal lecture, some people learn best by practical examples, some people learn best by one-to-one tutorials. There is no teaching method that suits all. And this is actually a challenge for teachers to do things that attract everyone. It's not easy. But the focus here is on product. The product. What are the graduates, what can they do at the end, not on the process. I'll give you the answer now, just to put you out of your misery. This is the answer. This is the minimum. So with a geological map and memoir, some tubes of soil from the site, a pencil and paper, you should be able to design a safe and economic slope and foundation. And when you go for interviews, an employer can test whether you can. Of course, postgraduates, you'd be able to do much, much more than that. And you would hope you would hope graduates from a first degree course in civil engineering could do more than that. But if they can't do that, it seems to me there's no point in asking them to do anything else. Now, geotechnical engineering is about building safe, serviceable, economic geotechnical structures, foundations, dams, walls and slopes. And things go wrong. These are classic, some of the classic failures in literature. You're probably familiar with some of those of you who studied the literature of things going wrong. Now, I want to distinguish very clearly here between experience and expertise. You talk about an experienced engineer. What that means is they've been doing something for a long time, probably slightly incorrectly. Nothing's gone wrong and they've been lucky. And part of the reason they've been lucky is the margins of safety in geotechnical engineering are absolutely huge. You have to make a major cock-up before something goes wrong, and it does. And people make major cock-ups because they didn't get the fundamentals right. Now, expertise is about getting the fundamentals right, and that's what I'm interested in. Somebody with expertise will say, this is the first time I've done this, I'm doing it properly, it will be fine. So just remember the difference between experience and expertise. And for you young ones, when the senior engineers quiz you over your designs, look them in the eye. Because you're probably better engineers than they are. Now, geotechnical engineering is not a standalone subject, despite what your university lecturers thought. They would ring-fence their subject. Structural lecturers would ring-fence structures. There's very little intercommunication, but there's a lot of common ground between these disciplines. And I'll show this later on. And really, it is all physics with a little bit of chemistry. Everything you do in engineering boils down to, everything in the way of engineering analysis boils down to physics. Geology and engineering, geotechnical engineering are of course obviously related. And you might think about the overlap between those disciplines. Geology describes the past. It's a logos, a cataloguing subject. It describes the geo, it catalogues the geo. It says, how did this material become like this? And so on. Engineering predicts the future. It says, how much will this foundation settle if we load it? Now think about that, because the whole of geological teaching is to do with the study of the past and interpreting the past. And geologists have a certain mindset as a result of their education. Whereas engineers are all to do with calculations and forward looks and what happens if we do this and that. And that gives them a certain mindset. And the trick is to see the overlap so the two work together. There's another thing to think about. Is the basis of geotechnical engineering empirical or is it theoretical? There are people who say that soil in the ground is so variable we cannot have a simple universal theory for soil mechanics. Therefore, we must test the hell out of everything and use empirical correlations. And there are others who say soil in the ground is really only a collection of mineral grains, rough or smooth, rounded or angular, arranged in a certain way. It is perfectly possible to have a simple theory, universal theory, that describes the behaviour of mineral grains. And it's not a question so much of what do you think about that, but what did your teachers think about that? Because that's what you think about. And I started my career at Imperial College as part of the top lot, and later on I was lucky enough to go to Cambridge and became part of the second lot. I bridged the gap. Now, process. How are skills manufactured? It's another way of talking about education. Think of education as a manufacturing process. So raw materials go into the factory. They are school leavers. They have basic maths. You can write an essay and you hope they can behave properly. And they go through this thing called a university that's a factory. It's turning raw material into a product. And the product is graduates in the construction industry. All that stuff about advancing knowledge and all that stuff. That's what happens. That's the real politic of education. Teaching and learning comes in a variety of ways, in a variety of words. It's just worth going through some of those. The syllabus, for you senior employers, is a list of topics covered, not necessarily skills gained. The process, as I said, it might be through lectures, it might be tutorials, teachers teach. They say what students have to learn. You have to do it yourself. Oh my goodness, that's fun, isn't it? I wonder what that was. Students learn, this is what they can now do, and the product of the graduates. And this is what they can do. So, some very basic basics. What everyone, engineers and geologists, should be able to do. And I suppose you can test yourself to see whether you can. Now, again, we've seen that one, and this is the crux of the talk. Geological memoir, choose a soil, do some simple designs, and when graduates go for a job, employers can test whether they can do that or not. They should be able to design a safe slope, and they should be able to design a serviceable foundation. In order to do that, they need to be able to determine appropriate parameters and do calculations with a pencil and a piece of paper. No computers. Because I come from a generation before electronics. I didn't even have a calculator. All I had were log tables and a slide rule. You know what a slide rule is, but the majority of those probably don't. right. But we know about that, don't we? Yeah, right. And I want people to be able to do these things. And engineers should do these things before they touch the first button. I'm not going to talk about retaining walls here. Retaining walls are difficult. And I don't think it's correct, I think it's appropriate to ask graduates, just people doing an undergraduate course, to really get to grips with the niceties of retaining wall design. You can get them to calculate earth pressures and all the rest of it, but there's no human known to man who can really get to the bottom of the stresses and displacements on a retaining wall. So it's not right to ask students to do it as well. So we're going to be dealing with slopes and foundations, essentially. There's a lot of common ground across an undergraduate course. Geotechnical analyses are very closely related to the basic analyses in structures and hydraulics. It is entirely wrong to ring-fence these subjects. There's so much overlap across them. They should really all be taught as common civil engineering. For example, the calculation for the ultimate limit state of a beam is very, very similar, and the principle is identical, to the calculation for the ultimate limit state of a foundation. There's some work done on the left, and there's some work dissipated on the right. It's the same in both cases. The analyses for the deformation of a simple cantilever of a beam are very similar to the calculations for the settlement on a foundation on elastic soil. There's a displacement, there's E's coming in, there's A's coming in, and if you look across those equations you can see the principles are just the same. And the principles for thinking about open channel flow, Bernoulli, there's the Bernoulli equation, are very similar to the analyses for flow of water through soils. If you look across, they're almost the same, except in seepage, the V squared term is neglected because the velocities are so small, and there's a head loss, P, in the Bernoulli equation, and energy is conserved. But they're very, very similar. And why should students come away from their course thinking that these are completely different subjects, completely different topics, with completely different analyses? Why shouldn't they be given the opportunity of seeing the overlap and developing their thoughts in that way? But the soils are different, and they're different in this way. The soil behaviour depends on pore pressure, Tazaki, so rates of loading and drainage matter. We'll see this in a minute. Strength and stiffness of soil vary with current, stress and strain, and so change with loading. We know about friction. You may also know about the decay of stiffness with strain. These two little things are those that make soils a bit more interesting than steel. I mean, steel is just not interesting. Now, concrete is moderately interesting, but that's only cemented soil. Now, this is the key one, isn't it? This is Tazagi's principle of effective stress. All I've written down there is the effective stress equation. That's what it is, and it's that stress that governs soil behaviour. That's the key. And luckily for us, you can calculate it as the difference between the total stress and the pore pressure. This is the total stress, that's the rest of the world applying loads to the soil, and that's the self-weight of the soil, and that's water pressure. And again, luckily, total and effective shear stresses are equal. When an engineer writes down an equation, it must contain all effective stresses, or all total stresses, or if there are total and effective stresses, they must be correctly related by the pore pressure. No. Just make sure that that happens when you write down an equation. I've seen many engineers mixing up total and effective stresses, and when challenged, they say, oh, it doesn't really matter, does it, John? I say, yes, it does. You must get that one right. Now, when you open your sort of standard sort of textbook, Craig, anyone? And you find page after page of sort of analysis that justifies the principle of effective stress. Well, most of those analyses are actually wrong, and you shouldn't be worrying about them anyhow. This is one of the things that you've got to take on trust, and it's better not to question why. That works, and that's all you need to know. It works well. Now, when soil is loaded, water has to squeeze out or not squeeze out. So we have two cases, and the question is, when soil is loaded, does the water move while the loading is being applied or not? So we have the two limiting cases. Here, the loading is drained because the pore pressure remains a constant with time. Then as the total stress increases, so the effective stress increases as well. If the pore pressure remains a constant, you know it, so you can calculate effective stresses, and that is an effective stress analysis, sometimes called drain, or sometimes called drain, that it is drain, sometimes called slow, and that's a misnomer. Welcome, you're not really terribly late, and it's all right. The rest of you will bring you up to speed later on. I know the room is hard to find, but there you are. We're only up as far as consolidation, so it's okay. So, and over here, the loading is applied so quickly that during the loading, the water has no time to move. In that case, the water pressures change, and the volume doesn't. And that's called undrained loading, and because we don't know what the pore pressures are, there has to be analyses with total stresses, and that is called a total stress analysis. And they must not be mixed. In the total stress analysis for undrained loading, undrained, quick, volume constant, there are pore pressures being generated which are now larger than the equilibrium pore pressures in the rest of the world. So if I stand on the ground quickly, all I'm doing is raising pore pressures, walking on water. All I do is raise the pore pressures, but the water out around me is still at the original pore pressure. There is now a hydraulic gradient. Water flows. And as the water flows, I gradually settle. And that's called consolidation. And as the water flows, the pore pressure decreases, and there it is. So after undrained loading, we get consolidation. Now, the pore pressure which is over and above the equilibrium pore pressure is the excess pore pressure, and it always has a little bar on it. Well, in my terms, in European terms, excess pore pressure has the bar on it. The Americans, bless them, put bars on top of stresses for effective stresses. Now, I'm never quite sure whether the Americans get to grips with excess pore pressures or not, because you can never tell. But I want you to be sure that you get those right. Now, in doing an analysis, you have to choose which of those you're going to do. And I'll explore in a minute how you make those choices. But I'll say now, in case I forget later, that if you can't decide whether your loading or excavation is going to be essentially drained or essentially undrained, you have to do both to be sure of getting the worst case. Or you can go and start pressing buttons and doing coupled analyses where the computer in some way applies load and allows dissipation at the same time, but you've got to do it with a pencil and a piece of paper first. So partial drainage, consolidation during loading is tricky, and it's well beyond any undergraduate required expertise. Rates of loading and drainage vary enormously. Down the left-hand side there are rates of loading. So an earthquake is of the order of 10 seconds. Okay, we can argue whether it's 1 or 100. Down to natural erosion, which 30 years is 10 to the 9 seconds. So not many of you are more than 10 to the 9 seconds old. Some of us are well over 10 to the 9 seconds. But there's a huge difference there in the time it takes to apply loads. Similarly, this is permeability. Now, if I said a K is 10 to the minus something, that doesn't mean anything. So what I've done here is to show permeability in how long it takes for water to flow 1 metre under a unit hydraulic gradient. In the gravel, it's around 100 seconds. In clay, it's around 10 to the 8 seconds. Again, this huge variation. For typical construction, 10 days to 3 years, you can dig a reasonable hole in 10 days, build a large building in 3 years. That's about it. Sand and gravel, which are coarse, can be considered to be drained because the permeability is so large the water flows during the loading, and we can do effective stress analyses. For silts and clays, they are fine-grained soils. We have to consider them to be undrained, so we have to do a total stress analysis followed by consolidation. Earthquake loading is up here, so even coarse-grained soils will be undrained during an earthquake event. That's how we get liquefaction. And natural erosion of a clay cliff with the sea or river nibbling away is so slow that the clay will be drained the whole time, and the pore pressures will simply correspond to a steady state flow net. But as engineers, you have to decide which of those you're going to use. And just notice we're talking about coarse-grained soils and fine-grained soils, drained loading and undrained loading. No mention here of cohesion soils and frictional soils. Soils are not either cohesive or frictional. Soils are either drained or undrained. Here is a coarse-grained soil being loaded in unconfined compression, and it's undrained. Here is clay being loaded in unconfined compression. The principles that give that clay its strength are the same as the principles that give that sand its strength. And you might like to ponder, we'll come to it later, why is the clay so much stronger than the sand? Students should be able to answer that. Down here there is the coarse-grained soil which is now drained, so it's at its angle of repose, and there is the fine-grained soil which is at its angle of repose. And there the young engineers are being amazed by clay having a friction angle. But you see what I'm saying? So engineering soils are simply a collection of mineral grains. They behave in exactly the same way, and what's controlling the behaviour is what's happening to the pore pressure. That's what the difference is in there. It's the pore pressures in these materials that are different. We'll explain why later on. Soil does not have a single strength. If you shear it, there will be the peak strength. It will reach a constant volume or critical state strength. And if it's a clay soil with the clayty particles, they'll all line up and we get a lower residual strength. So the soil has 3 effective stress strengths, and you can say it's just got one undrained strength that matters. So soil has at least 4 strengths. You can't talk about the strength of soil or the strength of a soil. It's got 4 strengths. And the engineer needs to decide which of those to measure and to use in an analysis. And graduate students should be able to do that because they know the fundamental principles of what's happening. Or we hope they do. Soil does not have a single stiffness, unlike steel, and we know that, that there is a rapid decay of stiffness with strain from very small strains, very large stiffnesses, down to very small stiffnesses near failure. And that's a very, very significant reduction in stiffness, and it matters. And it's really such an important feature of soil mechanics that needs to be explained and taught, introduced at undergraduate level. So graduates should be able to choose a total effective stress analysis, determine the appropriate strength, relate stiffness to deformations. They should be able to model the ground. What are soils? They're simply mineral grains with water. That's what soils are. Engineering soils are bad. gardener soils are a little bit different, but engineer soils are that. Rocks are like that, but they are strongly bonded and jointed. One of the tests you must do with a piece of soil is determine whether it is bonded, whether it is cemented or not. To do that, you put it in a glass of water. You put your soil sample in a glass of water and come back in 24 hours, and almost certainly if it's a soil, it's just formed a cone, because soils are not bonded. If it's slightly bonded, it will be very weak, and you can examine that by poking pencils into it. Rocks are strongly bonded and contain joints. That is the distinction between engineering soil and engineering rock. Are the grains bonded or not? Are there well-defined discontinuities and joints? Soils are grains that are not bonded, rocks are cemented soils that are jointed. The properties of soils depend on the grains. And whether we're talking about fine grained, coarse grained, rough or smooth. That's really enough from first principles to describe soil grains. And are the grains loosely packed or densely packed? So I want graduates to describe a soil in those terms. I want them to say whether it's a coarse-grained soil or a fine-grained soil or a well-graded soil. And I want them to be able to say whether it's loosely or densely packed. And that's all, because those things will tell you nearly as much as you need to know about the soil properties for routine design. There are a number of basic surface processes. There's weathering of granites in Hong Kong. There's erosion of a river valley in the Himalayas. There's transportation and deposition. There's transportation of materials in Canada and deposition of the gravels somewhere I'm not sure. Those are the fundamental mechanisms which create engineering soils. Climate determines the product of weathering. So when soils weather, when rocks weather, they weather into soils, and what is produced depends not so much on the parent rock, but on the climate. In hot, wet climates, there's enough heat and wetness to change rocks chemically. And you finish up with quartz sands, which are inert, and clays of some kind. In hot, dry environments, or in cold environments, there's not enough to get any chemistry going, but the changing temperatures every day simply expand and contract, expand and contract. If you took a piece of rock and put it in the oven every morning and in the fridge every night for 10,000 years, you would finish up with sand. And that's how sands are made. And they have the same characteristics as a parent rock, but the materials that are a product of chemical weathering are now quartz sands, which are essentially inert, and clays. Now that's, for you geology people, an extremely simple and simplistic view of the world, but it's enough for undergraduates to get a grip of what's happening. When you're looking at a site and you're looking at the soils, I want you to think about where it all came from. Where did the grains come from? How did they get to where they are? What has happened to them since they were deposited? And remember, because of plate tectonics and all this moving around stuff, everywhere has been somewhere else. Now, England is quite interesting in this respect because it's on a little bit of crustal plate that's just moves steadily northwards throughout geological time without sort of doing anything dramatic. There's been a few volcanic episodes, but it started off south of the equator, roughly where the southern African deserts are now. So our very early rocks, the Devonian, are sands. Then it moved up to the Congo, hot, steamy, and we go through the Carboniferous, our cold measures, and then we go to the Sahara, the Tertiaries, and then we go on through where the Mediterranean is now, the chalks, and that's why there is that sequence of rocks in England, because of the way that bit of crustal plate moved across the globe. So the question for a geologist, when looking at an exposure, is not, tell me, what is that rock? Because they give you a long geological name involving words like a quatern or like Carboniferous or something, which just tells you how old it is. What you should ask them is, where do I go in the world now to see rock like that being created, and what has happened to it since? Then an engineer should have enough knowledge of geology to piece together the likely properties and behaviour of that material, knowing its history in terms of climate, erosion, deposition. And that's the power of geology helping engineering in interpreting ground investigations. This is a very simple geological history. You get some deposition, you get some erosion, you get some more deposition, you get some more erosion, you get some more deposition, and you finish up with a profile like that one. And that's fine. And you look at that, without that pre-existing knowledge, all you see really is some rock, some stiff soil, some soft soil, and that doesn't, for me, give you the picture that you need. And it's just like that, really. There's a photograph of a land surface for which the geology underneath is like that. And that's a great help in interpreting the geological maps and the borehole samples. Engineers, graduate engineers, need to be able to evaluate design parameters. What friction angles should we take, and stuff like that. They should be able to, in order to start that process, they must be able to give an objective description of soil. And they've got to be able to describe the grading, the shape, and the roughness of the particles. It helps if they can describe the mineralogy, and it helps if they can describe the plasticity, the Atkinson limits. And they should describe the state, loose or dense. On Atkinson limits, it's interesting. You've got a liquid limit and a plastic limit. And the liquid limit is the water content where it's all wet and slippery, and the plastic limit is the water content when it's all brittle and crumbly. And you give an engineer a lump of soil and say, well, the plasticity of that, and they sort of fiddle about with it, and high plasticity that is, John, and low plasticity that's John. You can't do it like that, because what they're looking at is a lump of soil at a water content which may be anywhere between the liquid limit and the plastic limit. All they're looking at is the liquidity index. What you have to do is to get the sample of soil, rub it between your hands for a while, so the warmth from your hands evaporates some of the water until it's now at its plastic limit, where it's brittle and crumbly. You then add some water. You just add some water to it until it becomes soft and slippery. And you will either have to add only a few drops if it's a low plasticity soil, clays with lots of silts in, only a few drops, because the difference between liquid limit and the plastic limit is now very small. But if you have to add a lot of water, sometimes nearly as much water as you've got soil, that is now a high plasticity soil. And I don't want to see people just taking this sample and rubbing it in all high plasticity, that's on. They can't do it like that. You've got to do it by examining the wettest bit and the driest bit. Next time you're talking to an engineer, try it on them. That's all. But you know better because you heard it from me. You should be able to draw a grading curve by eye. You should be able to draw a simple grading curve just by looking at the soil. You can discover what the largest grain is quite easily. You can separate out into grains you can see from those you can't see, and that's roughly 0.1 of a millimetre. So you've got that point and that point, and just draw a bloody line through it. The grading curve isn't going to be much different from that. But do it. Do it. What is the grading of your soil? If you want to be clever, put it into a cylinder full of water, shake it all up, put it down, and the coarser grains will sediment first, and then etc. So you can't see it on that slide, I'm afraid, because the lights are up, but the soils here are gravels, then you go the coarse gravels, then you go to medium gravels, coarse sand, fine sand, medium sand, silts up there. Anything left suspended after 24 hours or so is essentially clay, and anything left floating on the top of the water is organic material. Engineers, ground engineers, should have one of those and a glass of water on their desk. Not for drinking, but for sticking samples in. And you just do not see it, do you? You should describe the grains, and the grains, the ones you can see, the grains will be, the grains will be either smooth and rounded, or they'll be rough and angular. And all this sub-rounded and all the rest of it, don't bother. It's either smooth and rounded because it's being worked in water, or it's rough and angular because it hasn't. And for simple purposes, that's all you need to do. They don't teach you that at university, do they? Some parameters depend only on the grains. They are material parameters. The constant volume or critical friction angle is one of them. For soils which are fine-grained, you can't see the grains. If they're lower PI, we know about that, the friction angle will be sort of in the high 20s. If it's high PI, we know what that means. It will be in the high teens, and anywhere between, it's roughly linear. London clay's in here somewhere, and the friction angle is 24 degrees. You can do it, why not? And you probably won't get a much better answer by chucking money at triaxial tests. For coarse grained soils, if it's smooth and rounded, it's 30 degrees and blah, 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 blah. It's just simple. Students graduating should be able to do these things. They should be estimate the current state between dense and loose. When a fine-grained soil is at its minimum water content, as we saw earlier, it's at its plastic limit and it's crumbly. When it's at its maximum water content and it's still soil, it's soft and floppy. Those are liquid limits, and in between is the liquidity index. For coarse grained soil, the equivalent ones are the maximum and minimum density, and in between those are the relative density. Just notice the numbers go the other way. I mean, ground engineering is perverse, isn't it? That goes from 0 to 1, and that goes from 1 to 0. But a graduate engineer should be able to, from a sample of soil, make reasonable estimates of what its liquidity index is, where it is on those in those ranges. And there are simple parameters that depend on where it is. The undrained strength of soil at its plastic limit is about 200 kilopascals. It is. The undrained strength of soil at its liquid limit is around 2 kilopascals. There's a linear relationship between the Atterberg limits and the log of stress. So knowing the liquidity index, you can make reasonable estimates of undrained strength. And graduates should be able to do that. There are simple relationships between angles of friction and relative density. And again, graduates should just be able to do these simple things. And you won't get significantly better answers by throwing money at laboratory testing. You might get slightly better answers, a degree or so here and there, but they won't be substantially different to those. So graduates should be able to describe a geological history, create a three-dimensional geotechnical model, and estimate design parameters from soil descriptions. They don't have to be able to do a triaxial test. In fact, there are very few of us who can do a reliable triaxial test. I say of us. Right, towards the end. They should be able to design simple slopes and foundations. Now, the basis of geotechnical design, any geotechnical design, is this. You have to consider loading and drainage. If you believe the soil to be drained during your construction, you know what the pore pressures are, and you can do effective stress analyses. If you don't, it's total stress analyses. There are two distinctly different branches of calculation. One is to calculate an ultimate limit state, collapse, failure, and that is a plastic calculation. And there is another calculation which is to do with deformations at working load, and for simple geotechnical design, that is an elastic calculation. And then there are criteria for acceptance. How do we accept a design? The factor of safety for an ultimate limit state is typically 1.25. The factor of safety for a serviceability limit state design is typically 3, or the load factor is 1/3. I used to go around being a mischievous. I've grown up being totally mischievous, but I'm still a bit mischievous. So I ask engineers, look, you design this big slope, this major earth dam, with a factor of safety of 1.25. Oh, boy, yeah. And then you go and design the foundations for a small house with a factor of 3. Why do you do that? And you'll be surprised the sort of waffly answers you get. And the answer is this. For the slope, we don't mind how much it moves, provided it doesn't move a lot. So the factor of safety is just that. It is a factor to ensure safety. For the foundation, though, we don't want it to move very much. And if it doesn't move very much, it won't move a lot. And we know, by chance, that if you calculate the ultimate load and divide by 3, you will be in a range of action where the movements are small. And that's the reason for that. So the factor there is nothing to do with safety, and we should stop calling it a factor of safety. It's a load factor, and it should be 1/3. How do you design a slope or a foundation? You can either do it with a pencil and paper or with a software program. The former is reliable, the latter may be more accurate, but it's not more reliable. And engineers should be able to do the first. And they should do it before they do the other. All you need to know is that, critically, most slopes fail with slipping fairly shallow. In that case, it's an infinite failure case. If the slope is dry or totally submerged, the critical angle is the angle of friction. If there is steady state seepage, the critical angle is a half the friction angle. And if you're really excited, you can go into the textbooks and find out why. And the question now is, what strength should you put in here? Is it the peak strength, or the constant volume strength, or the residual strength? If you know there are old landslides there and old surfaces in clay, it's got to be the residual strength. Otherwise, you can choose. Conventional practice puts in the peak strength with a factor of about 1.25. But a much more sensible way is to take the critical state strength, the constant volume strength, with the worst credible pore pressure and a factor of 1, just over 1, because it can't get worse than that. By definition, you've chosen the worst credible pore pressure, so it can't get worse, and the critical friction angle is the lowest it can get, except if you get a residual. So my advice to engineers and to students, graduates, is to make sure your slope stands up with the critical friction angle and the worst credible pore pressures, and the factor is a little bit more than 1. And if doing routine designs it gets to be steeper than that, then you've got to declare where the extra strength is coming from. And you won't be able to. Best do it like that. So all you need to know is I equals phi, or I equals a half phi, and they are the constant volume, critical friction angles, which we've seen earlier on, are closely related to the grains. Sand, 30 degrees, and all the rest of it. Easy peasy. People should be able to construct a reasonable flow net in which they can determine the pore pressures and rates of flow. And there is seepage coming out of this slope. And here's the young engineer building his dam, and he's noticing water is seeping through the dam. In this case, he's got a critical hydraulic gradient. There's been erosion there at the toe, and the dam is breached, and there's death and destruction all down the valley, and there's the remedial works going on. The point of that is children often know a good deal more practical soil mechanics than any number of qualified engineers. Rock slopes is essentially geometry, and blocks can slide or blocks can topple, and we're just not interested in the strength of the rock material for practical purposes. If you're mining at kilometres down below the ground, then of course the strength of rock matters. But for normal civil engineering purposes, the strength of fresh rock doesn't come into the equation. It's geometry, and people should know that. A shallow foundation will require small movements. So this is a simple design based on the bearing capacity and the load factor. So we're going to calculate the bearing capacity, that's here somewhere, and we're going to divide that by 3, load factor was third, and that will bring us to a point in the load settlement curve where the strains are of the order of 0.1%, which is 10 millimetres for a foundation of 10 metres wide. So that order. Now, just notice this, and the actual load settlement curve for a foundation does something like that. And if you keep on loading, it will go on and on and on. You can keep on loading a foundation deeper and deeper and deeper, and it just turns into a pile. So what is the bearing capacity of a foundation? There is no such thing, you just keep on loading, providing it doesn't rock over. So the bearing capacity of a foundation is actually only the answer to a calculation. That's what it is. And the calculation we do is a simple plastic one that gives us this bearing pressure at failure is 6 times the undrained strength, the load factor of 3, the design pressure is 2 SU. And really, that's all you need to know at this level. You design foundations on clays, 2 SU. We talked about consolidation, and what people are interested in is the magnitude of the final settlement, and that's related to this compressibility parameter that I haven't gone into now. And it'll certainly be told to engineers, probably. And what's equally interesting is how long it takes for consolidation to occur. And the time of consolidation is simply h squared over cb. And again, those two little equations are really all you need to know about to design the settlement, the time-dependent settlement of simple foundations. That then is John's basic undergraduate syllabus. And you could probably teach that in the first term, including practicals and things like that. And if you do give them that, then they're well on the way to becoming good, proper ground engineers that don't make mistakes. And I'm just going to show you 1 or 2 examples of people making mistakes. And I'm showing you these so you won't make these same mistakes. It's all right-ish to make a mistake. It is certainly not all right to make the same mistake twice, and it's not all right to make the mistake that you've seen somebody else make. So I'll show you some mistakes, and now it's not all right for you to make these mistakes. Very quickly, I'm sorry, I'm just overshooting a bit, I'm in a couple of minutes more. So soils are not either cohesive or frictional. The mistake is to describe soil a cohesive soil. Well, there is sand being cohesive. It's got an unconfined compressor strength. There is clay being frictional. Please do not talk about cohesive and frictional soils. Please talk about soils that are coarse-grained or fine-grained, because that controls the drainage and that controls whether you will be doing total stress analyses or effective stress analyses, whether you need an undrained shear strength or whether you need a friction angle. Cohesion C dashed and undrained strength SU are not the same thing. There is a sample of sand in an unconfined compression test. There is its Moore's circle. That is its undrained strength. If we confine that sample of sand and apply radial stresses, provided it has the same water content and volume, the Moore's circle will be the same size. So the shearing resistance is equal to SU, the undrained strength, so long as the water content hasn't changed. Do not use CU, because then you start talking about cohesion, and it's not cohesion, it's undrained strength. For effective stress strength, you can pour the stuff into a heap. Here I've got it in a rotating cylinder, so it forms a continuously deforming slope, and that is the friction angle. Always take C dashed equal to 0 unless the soil is strongly bonded or welded together, in which case you're going to be dealing with rock mechanics. This is the unconfined compression test, which you can amaze your mum with. You do the test, you put the bucket on there, you load it until the sample fails. You can now draw the Moore's circle of total stress, because the radial stress is 0 and you can calculate the axial stress from the height of gravel in the bucket. So you can now draw the Moore circle of total stress. Below is the Moore circle of effective stress. You can dry the sand out, pour it into a heap, and get the friction angle. And the Moore circle of effective stress must have the same diameter as the Moore circle of total stress, and it must just touch the envelope. And the horizontal difference between those two circles is the pore pressure. We have just determined the suction, the negative pore pressure in a sandcastle. And it's the suctions that give it the sand the effective stress coupled with the friction angle it needs to stand up. And you can do the whole thing at the seaside and draw the graphs in sand with your finger. And I've done it many times. In order to determine whether the soil has a cohesion, you put it into a glass of water and wait. If that happens, it's clearly cohesionless. If that happens, you poke it with a pencil, and it will almost certainly, if it's a soil, it will be very soft and weak. You must wait 24 hours at least for that, for this to happen. If it's still strong, then it's no longer a soil, it's a soft rock. And we're going to be doing something other than soil mechanics calculations. Because soil mechanics deals with uncemented collection of granular material, or only weakly cemented. People misunderstand the purpose of factors, and I went through that earlier on. And the purpose of factors is very different. So these are the common, simple, conceptual mistakes that I find ground engineers doing too frequently. And we need to get the young and get them to educate the senior people. So that was it, that's where we've been, and thank you very much for listening so patiently, and thanks very much.
Thank you very much, John. I guess this is the point where we throw it open for questions. Has anyone got any questions for John? Covered it nice and simply for everyone.
They're all zapped and thirsty, I can
No, thank you very much for that presentation. It was a really great simplification of grilling, and should hopefully help a few people.
Thank you very much indeed.